So we're always going to try direct substitution first. And that's the same strategy we use in Calculus 1. Always just try to plug your values in first and see if you get an answer. So if we're asked for the limit, since we have two independent variables, they have to give us values for both of them. We've got to replace both of them. So they're going to say as x, y approaches, and they've got to give us values for both, since it's a function of two variables. Always just try direct substitution first and see if you can get an answer. So as xy approaches to -1, we want to know where the function 2xy over y plus x looks like it's going to. So we just plug in 2 for x and -1 for y and see if we can get an answer. In the top, we got 2 times 2 times -1. In the bottom, we've got -1 plus 2. So that's -4 over 1, which is -4. The limit as xy approaches 0, 3 for 2xy over xy minus 2x. Always try direct substitution first and see what happens. Okay. Zero over 0, which is indeterminate. 0 over 0 is indeterminate. L'Hopital's, we do not have a L'Hopital's rule for functions of several variables. But this one, there is a common factor, correct? But on this one, there is some algebra that we can do to fix it. One of the cases that leads to 0 over 0 is a common factor. And we do have a common factor of x here. So we can pull out an x and cancel it away. Yep. So we factor out of x, and then we have a common factor of x in the top and the bottom. And when we pull it out and cancel, we're left with 2y over y minus 2. And now we can try to plug in again. We only have y's left. And what did they say our y value is approaching? 3. It's approaching 3. Yep. So this is 2 times 3 over 3 minus 2, which is 6.
There'll be a hole there.
There is a hole, yep. When you can factor and cancel, it creates a hole in the graph. So what we did here is we checked for an algebra solution to the indeterminate form. Zero over 0 sometimes, not all the time, but 0 over 0 sometimes means that there's a common factor. In Calculus 1, to show that a limit exists, we had to show that the left-hand limit and the right-hand limit were doing the exact same thing. So if this is the graph for f of x, we had to show that the limit as x approaches a from the left and the limit as x approaches a from the right for f of x were equal. If they were different, that means there was a gap in the graph. That means on the left we're approaching one value, but on the right we're approaching something completely different, and there is this big old gap. And if there's a gap, that means the limit does not exist. And that's because on the x-axis is just a number line. It's one-dimensional. So all it has is a left and a right. When we jump to three-dimensional space, and our domain now is a set of ordered pairs, we're working with the entire plane. And there's not just a left and a right anymore. In order to prove that a limit either exists or does not exist, we can't just show that it comes from the left and the right to the same spot in the plane. In the plane, it can come from an infinite number of directions. And this is really hard to draw. But if I wanted to approach the origin, those are all straight lines too. We don't have to come in on a straight line. I can come in on a parabola. These are all flat on the XY plane. All of those red arrows are flat on the XY plane, trying to approach 0, 0. We have to show that if our limit exists, that all of those directions, that the limit is approaching the same value. That would be impossible because there are an infinite number of paths that approach 0, 0. So really what this is more useful for is a proof by contradiction. We can prove that the limit does not exist if we can find a path that the limit comes out different. If any one path gives a different answer, that means along that one path there's a gap. So the limit doesn't exist. So our plane consists of an infinite number of paths that can approach a single point. And the limit on every single one of them has to be the same if we want the limit to exist. But because there's so many, it's really going to be impossible for us to do. So really, what this is going to be more useful for is for us to show that it does not exist by finding a path where the answer differs. We're going to prove that this limit does not exist. The limit as xy approaches 0, 0 for x squared y over x to the 4th plus 4y squared. What do we get if we try direct substitution? We get 0 over 0, which is indeterminate. They could have a common factor, but look at your denominator. The denominator is a sum of squares, and our two terms don't have anything in common. So there's not going to be anything we can do factoring wise in our denominator. We're going to show this by approaching 0, 0 along different paths and showing that we get different answers along different paths. So we cannot fix this one with algebra. So we're going to pick a path in the xy plane that goes through the point 0, 0. And by path, I just mean an equation.
Y is X.
Y equals X goes through the point 0, 0. You could either replace all the Y's with X's or you could replace all the X's with Y's. It's up to you. So we replaced all the Y's with X. And now it's just a limit with one variable. It only has X. So when the limit as X approaches 0, it's still 0 over 0, but now we can do algebra. What kind of algebra can I do in the denominator? We're going to pull out an X squared. And then we can cancel X squared in the bottom with 2 of my X's in the top. And now it's the limit as X approaches 0 for X over X squared plus 4. And this is not indeterminate anymore. Direct substitution gives me 0 over 4, which is 0. So along this path, along the y equals x path, it's approaching 0. Now we need to find another path where we get a different answer. We need another graph in the xy plane that goes through 0, 0. Y equals x squared also goes through the point 0, 0. So that means we're going to replace all the y's with x squareds. So go back to your original. Replace all the y's with x squareds. So in the top we have x squared times x squared. In the bottom we have, oops, I made a mistake. In the bottom we have x to the 4th plus 4 times x squared squared. So all I've done is I've replaced my y's with x squareds. So this is x to the 4th in the top, x to the 4th plus 4x to the 4th in the bottom, which is really 5x to the 4th. And those x to the 4ths can cancel. What's this limit? 1/5. We found a different path that gives a different answer. That means at 0, 0, there is a gap in this graph, which means the limit does not exist. Well, there is a trick. Usually we want to be able to combine these terms so that we can do the algebra to simplify it. So in the bottom, if I want my x to the 4th and my 4x squared to eventually be able to combine, that's not what the right thing I'm looking at. If I want to be able to combine these two terms, then I need my y squared to turn into an x to the 4th. So to make them combine, I need my squared to turn into a 4th. So I need to plug in a squared there. If you square a square, it turns into a 4th. So there is some kind of thinking ahead with your algebra to figure out what's going to work and what's not going to work. Usually, you can always do y equals x and get a baseline. And then You need to do a little bit of thinking ahead with your algebra of, if I want those terms to combine, what do I need to do? If I need my squared to turn into a fourth, then I need to square a square, so I need to use the square function. This one also does not exist. Algebra will not fix it. Direct substitution is indeterminate form. We're just going to jump right into our paths. You need to make sure that your path goes through the point that you're doing the limit for. So we need to make sure that we pick a path that goes through 0, 0. So somebody give me a path that goes through 0, 0. Y equals x. So I'm going to replace all of my y's with x's. And what do we get for our limit? So we get 1. So now we need to make sure we don't get 1 next. So we check another path. If we do get 1 again, then we just have to do a third one, or a fourth one, or a fifth one. Y equals x to the fourth. Okay. So we're going to replace all the y's with x to the fourth. So I'm going to go back to my original. Let's see what happens. So 2x times x to the fourth over x squared plus x to the fourth squared. So that's 2x to the fifth over x squared plus x to the eighth. And direct substitution 0 over 0, but we can do some algebra simplifying now. We're going to pull x squared out of the bottom, and we can cancel it with 2 of them in the top. So now we've got the limit as x approaches 0 for 2x cubed over 1 plus x to the 6th. And we get 0 over 1, which is 0. 2 different paths approaching the same point, and we got 2 different answers. That means at 0, 0, there is a gap in the graph. That means the limit does not exist there.